In order to truly understand the value of data structures, we have to go deep down into the way a computer works at the fundamental level. In order for a computer to run code, it needs to keep track of things like variables, like numbers, strings, array. These variables are stored in what we call random access memory, or RAM for short. That's how programs run. We remember this from space complexity video, right? On top of that, we also have storage, where we store things like our video files, music files, documents. And the storage can be a disk drive, a flash drive, or a solid state drive. Data on storage is permanent, or what we call persistent. So when you turn off your laptop or computer, it's still going to be there when you turn it back on. In RAM, you lose the memory when the computer turns off. So why wouldn't we just always use storage so we don't lose any data? Well, the problem is that persistent storage is slow. Because you see, a computer is run by its CPU. You can think of the CPU as the little worker that does all the calculations that we need. It does the actual work inside our computer. And this CPU needs access to the RAM and the storage. But it can access the RAM and the information in the RAM a lot faster. But let me give you an example as if we're using Google. When we run Google Chrome, for example, a browser, that Google Chrome browser has a piece of code. Now here I've simplified it, and we just have a variable a equals 1. We're just assigning this variable 1. But we can imagine how we have hundreds, thousands of lines of code of Google Chrome. Now, in order for our computer to run Google Chrome, we run the CPU for it to do so. Now, when a variable is declared in, let's say, a script to run Google Chrome, it's going to hold that in memory, in our random access memory. But once we turn off or close Google Chrome, we want to be able to reopen it, right? Well, that's what we do when we save an application on our computer. We save it to storage so that next time we open up Google Chrome, the CPU is going to grab the program from the storage so that it can use it again. And for Google Chrome to run fast and run smaller scripts, it's going to keep that information in random access memory. We can see this on our computers as well. If I go to About this Mac, my computer, we can see here that we have the processor, which is my CPU. We have my memory, which is my RAM. And if I go to storage, this is my flash storage, my persistent storage on my computer. So you can think of RAM in the computer as a massive storage area, kind of like a data structure, right? Well, this massive storage area has shelves that are numbered. We call these addresses. And it's a really, really big shelf that holds a lot of information. And it allows us to run programs on our computer. Now, each of these shelves holds what we call 8 bits, or numbers. If you see here, 1, 2, 3, 4, 5, 6, 7, 8. Each one of these numbers is a bit. And a bit is a tiny electrical switch that can be turned on or off. But instead of calling it on or off, we call it 1 or 0. And 8 bits is called a byte. Each shelf has 1 byte of storage. And the CPU is connected to something called a memory controller. And a memory controller does the actual reading of this memory as well as writing this memory. Because sometimes this shelf might be blank and doesn't have anything. Now, this direct connection to the CPU is important because the CPU asks the RAM, hey, what's in shelf number 0? And the memory controller actually has connections individually to all of these shelves. Again, that's really important because it means that we can access the 0 shelf and immediately access the 7th shelf or 10,781 shelf without having to climb down or step down. That's what the name random access memory means. We can access memory really fast because we have these connections any shelf we want. We just need to know which shelf we're looking for. We can access the bits at any random address in memory right away. Even though this memory controller can jump between far apart memory addresses really fast, programs tend to access memory that is nearby. The closer the information is to the CPU and the less it has to travel, the faster a program can run. So computers are actually tuned to get extra speed boosts when reading memory addresses that are close to each other. For a computer to access 0 and 1 is a lot faster than a computer for it to access 0 and 1,000, because these are a lot closer together. And to further optimize this, our computers also have what we call a CPU cache, where the CPU has a tiny, tiny memory where it stores a copy of stuff that is really, really recent. And this is called a cache. A common one that you might hear is something called LRU cache. So again, if we use Google Chrome as an example, we turn on Google Chrome with, let's say we have the application downloaded on our storage. The CPU loads it up. And because we've visited hackernews.com, it's going to load up the information for that Hacker News and put it into memory, or maybe even cache, if it can hold it. So, why is this important for data structures? Well, data structures are, remember, ways for us to store information. For example, if we want to store variable a equals 1, well, in our modern computers, usually we represent integers, that is the number 1, in 32 bits. That is this block size of RAM. And by the way, this is now can be 64 bits with more and more recent upgrades. But this way, we can store the number 1 within this blocks of 32 bits. Why 32 bits? Because 8 bits, which is 1 byte, times 1, 2, 3, 4. So 8 times 4 is 32 bits. We can store 32 bits of information. And this bit of 1, you can see here, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 1 is stored now in memory 0, 1, 2, 3, or the address 0, 1, 2, 3. If we have another variable, b equals to 7, we would store it in the next block over here in our RAM. And doing this, you can now think about how systems that are 8-bit can hold 255 bits of information. Things that are 16-bit, well, they can hold a lot more information. And now we have systems that are 32 bits. You can see here that we can hold a ton of information. And then if we had 64 bits, that is, instead of having 4 little shelves over here, we have 8 shelves. Shelves times 8 bits. Well, that's a lot of information that we can store. And the bigger this is, the more diverse that information is. If we had an 8-bit system, well, the number 256, we can't really store that. That's really hard to do. And I can demonstrate this to you with JavaScript. You see, there's something called integer overflow. Now, JavaScript technically doesn't have integers. It only has what we call a 64-bit floats. But the idea is that a computer can only store a certain number of information. So using this syntax in JavaScript, we have math.pow, which is a function that returns the base to the exponent power. That is, the first parameter is the base to the power of the second parameter. So we can create really large numbers like math.pow, so 5 to the power of 100. If I run this, we see the number over here. If I increase this to, let's say, 6, again, another large number. Now, what if I keep going and change this to 6 to the power of 1,000? We get infinity. What is that? Well, as the number becomes too large to store in our RAM, then we need to represent this number that we cannot store into something that is tangible. In JavaScript's case, it is infinity. We can only store this much information, and no matter how big I make this, any number above a certain threshold is going to just say infinity. How cool is that? Now let's go back to the slides. I showed you all of this because other data types other than numbers work the same way. Each data type has a number of bits associated with it, and that needs to get stored in the system. And the system allocates that storage, and then the CPU reads from that storage. Now, I'll leave a link for you after this video so that you can get more information if you want. We don't want to get too deep in this. But a data structure is this. A data structure is an arrangement of data. You can define the way you interact with this data and how it is arranged in RAM. So some data structures in RAM are organized right next to each other. Some are organized apart from each other. And they have different pros and cons on access and write. Our goal is to minimize the operation that we need to do for the CPU to get the information, for the CPU to write information. And that is why data structures are so powerful. We're thinking about the low level. And I don't know about you, but this to me, when I learned about this, was really, really exciting. Because we have a way now to think how data structures actually affect the process of our computers, and how we can use what we know about computers now to write great code. I'll see you in the next video.